In the previous section, we talked about tuples. In case of a tuple, the role of each component of a tuple is determined by its position. And this may be a source of possible errors, since it's easy to make a mistake there. So, what if we could give names to the components? Record types allow us to do that. We can give a name to each component. And this makes code more readable, because field names have more meaning than positional reference. Let's take a look at a tuple example first. In the previous section, we defined this function getFirstName, which returns the first name value of a tuple. When we call this function, we made a mistake, since we passed our tuple values in the wrong order. We accidentally passed the occupation as the first component of a tuple, and our function returned the occupation instead of the first name. Unfortunately, the compiler wasn't able to catch this semantic error. Let's take a look at how using a record can help us to avoid this error. We declared a person record, which is composed of 3 fields: first name, last name, and occupation. And all 3 fields are strings. Then we created our look record, which has a type of person. You can see it has the same structure. Then we defined the getFirstName function, which takes an argument of type person and returns its field firstName. Finally, we passed our record as an argument to our function and got back the first name. As you can see, we are accessing records field using its name and not its position. As a result, we can't make the same mistake we did with a tuple, since accessing the field using its name is much safer than accessing it using its position. If you didn't understand this example, don't worry. We will now talk about records in much more detail. When creating a record, we need to declare its type first. To define a record type, we encapsulate field type declarations inside curly braces. Here we declared the record type named person. It's the same one we used in the first example. It contains fields of first name, last name, and occupation, and all of them are strings. Compared to tuples, record types must be declared first. We need to do that in exchange for the extra checks that the compiler is doing for us. When defining a record, we also need to make sure that all the record field names must be distinct and ideally not used in other record types. Since we declared the type of our record, we can now create one. Awesome! We created our first record called look. As you can see, it has the same fields as our person record type: first name, last name, and occupation. When we run this code, you can see that the compiler inferred our look record to be of type person here. Now, let's take a look at how to access the fields of our record. As you can see, we use a dot notation to access a specific field of the record. First, we write the expression that evaluates into a record, a dot, and after that, the name of the field we want to access. In our example, we accessed the last name field. To extract several fields of a record, we can use pattern matching, or in other words, destructuring. As you can see, we are using len binding for our pattern matching. In order to extract several fields of a record, we need to enumerate all the fields that we want to extract using curly braces. And for each field, we have to specify the pattern that is used to extract this particular field. When destructuring, we don't have to enumerate all the fields of the record, only those that we want to extract. In this example, we extracted last name and occupation fields of our look record. However, we are extracting values from a simple record. Let's define a nested record and extract values from it using a more complex pattern. We declared a new record type, parents, with father and mother record fields. We nested it inside our person type, here. Then we defined our two records, look parents, and nested it inside the look record. Finally, we use destructuring to extract the father value from the nested record. First, we extracted the parents record out of the look record, and then we extracted our father value. As you can see, we have to specify the pattern that is used to extract this particular value. We can also do this destructuring using a function. This function takes an argument and extracts the nested field of father out of it. As you can see, the compiler inferred that the type of the argument is the person. When we called our function by passing our look to it, we got back the value of Luke's father, Anakin. We can also update our records. However, since records are immutable by default, we need to create a new record from the old one. And we can do that using the spread operator. Let's update our previously defined record. The spread operator is represented by 3 dots. We created a new record by spreading the old one here and updating the occupation field. So in our new record, the occupation is not Jedi anymore, but farmer. We need to keep in mind that the original record still exists and it's unchanged. However, we can't use the spread operator to add new fields, as a record's shape is fixed by its type. That means we can't add a new field to our record. We can just update the existing one. We can write our code more concisely using so-called punning for record types and values. Punning is the syntax shorthand we can use when the name of a field matches the name of its value. Let's update our previous example to see what the punning is. As you can see, we renamed our record containing Luke's parents to parents. We still have our person type. Then we defined the parents record and we nested it again inside the Luke record. However, because the name of the field and of the value is the same, we can pun the parents field. As you can see here, instead of writing parents:parents, we can just write parents. However, we need to keep in mind that we cannot use punning for a single record field. Punning also comes in handy when converting from a tuple to a record. We defined a conversion function that converts a tuple with 3 string values to our well-known person record. Then we called this function by passing it a tuple as an argument. And we got back a record with 3 fields: first name, last name, and occupation. As you can see, punning makes our code more concise because we don't need to duplicate the names of records fields and values. As we've already mentioned, in case of records, the compiler provides us with the many checks which help us to write safer code. Let's take a look at some of them. When we use the record type declaration, the compiler can detect a typo in the field identifier at the compile time. Here, we made a typo when defining the first name field by writing it using camel case. And the compiler detected it. Moreover, it even provided us with a hint. When creating a record, we need to define all its fields. Otherwise, we will get an error. Here, we failed to define the occupation field, and as a result, we got an error with a helpful message. The value of each record field must be compatible with the field type as declared by the record type definition. Again, the compiler is able to detect this error at the compile time. Let's take a look. In this example, our occupation field contains a value of an integer. However, this isn't compatible with our type declaration, where we define that the occupation field should have a type of a string. As a result, we got an error. Reason's compiler is pretty smart, and it does its best to infer the types of our records properly. Let's take a look. In this example, we modified our good old person record type by removing the occupation field and adding the isJedi field instead. Here. We also created our record. Then we declared a new type called T, which has a single field, isJedi, which has the same name as one of the fields in the person record. Finally, we created a new record with a field isJedi. As you can see, the compiler inferred that this record isn't of type person with missing fields, but of type T with the right field. Let's continue with our example. We created another records type definition, X, which has a single field isJedi. This means that it has the same name field as the type T. However, while in one case this field is type of a string, in the other it's Boolean. And when we run this code, we got an error, since this record has only one field, which is a string. However, the compiler is checking the type using the latest definition of a record, which in our case is X, where the isJedi field has a type of a Boolean and not a string. The compiler isn't able to guess which type we want to use if both types have a single field with the same name. And this is the reason why we should try to avoid using the same field names in our records. We need to remember that in Reason, we cannot define a general function that takes any record type as long as it has a particular field. Here, we created two types, person and animal. They both share the field first name. Then we also defined a function called getFirstName that extracts the first name from a record. You can see that the compiler inferred the type of our function in a way that it expects the type animal as an argument. Let's create both records and try to pass them to our function. We defined the person type record called look here and the animal type record called the ragdoll here. When we passed our animal record to our function, everything worked and we got back first name. However, when we passed the person record, we got an error. And the compiler is telling us that our function works only when its argument has a type of animal. This means that we cannot pass different records with the same field name to the same function.